Okay, kids, this is the third time I'm going to try and give this lecture. The first time I went through the entire thing, got done, got an error message that said it failed to save. And this is a long, brutal lecture to give. So then I thought, second time, I'll just try and do like the first third of it and make sure that it's recording. Tried that. Still got the same error message. So, of course, Google to the rescue. I said, just turn off your computer and turn it back on. So I've tried a little short lecture just to make sure that it worked, and it did. So if you're getting this, then you know that it worked. If you see a news flash that says, physics teacher loses it and throws iPad into Cheney Lake, then you'll know that this didn't record the third time. So let's be optimistic that this might actually work at this point. So this is Louis de Broglie. It is not Louis de Broglie. Okay, it is not de Broglie. Okay, and if you like broccoli, you're dead to me anyway. So you kind of need to know this in terms of the sequence. So in 1924, and de Broglie was a French nobleman, so he really didn't have, a whole lot going on, but he did serve in World War I, so, kudos to that. So in 1924, he published this paper called Researches on the Quantum Theory. So you got to understand, this is like in history, this was the time when everybody was wanting to do quantum mechanics. This is the real exciting time. They discovered the electron, the proton, so all of the great science was being done at this time in quantum mechanics. So he published this in 1924. Basically what he says, and we'll go through the math in just a second, but basically what he said is that an electron can travel as a wave, as a wave of matter, which was counterintuitive to what everybody thought, because everybody thought, okay, hey, an electron is a bit of matter, it should travel in a straight line. It should not travel in a wave-like function. So he predicted it, and then in 1927, Davison and Germer actually shot electrons and discovered that just like light, when you do like a double slit experiment with light where you see like bands of dark and light, same thing happened when you do electrons. So the only way that can happen is if electrons have wave-like particles. Or properties, excuse me. So in 1929, he was awarded the Nobel Prize for discovering what was called the wave nature of electrons. So we're going to go through some hocus pocus on some math. Now, here's what everybody says when we get done. It's like, he won the Nobel Prize for this. Well, it wasn't so much that what he did, but it was predictive in nature, and he actually did the work to actually predict and verify his results. So let's start with momentum, mass times velocity. Now, the other side of this is that this was important. This was done after Einstein had published his works on the theory of relativity, which is, what Keaton brought up today. And that's E equals mc squared. So this is the speed of light, 3 times 10 to the 8th meters per second. And that's going to get squared, which right away gets you to the 16th power. So what this relates to is, and this is what we'll study, where you take hydrogen in the sun and it combines to produce helium. Well, in this process, a little bit of mass is lost, and that gets converted to energy, and we have this bright ball of light that we orbit, which is kind of cool. Without it, we wouldn't be here having this discussion. So this is happening billions upon billions of times every second, where we get energy from the sun. Now, the other side of that is that you have the energy of a photon, which is HF, which is also hc over lambda. So de Broglie took an idea of momentum, Einstein's work with energy, and then Planck's constant with light. So he's kind of merged all of this into one synthesis idea. So this is where we're going to do some hocus pocus. So we got momentum is mass times velocity. I want to take Einstein's equation of E equals mc squared, and I'm going to solve that for mass, and I'm going to get E over c squared. So then I'm going to do some hocus pocus. I'm going to take this and put that in for mass. So then I'm going to get E over c squared times v. Okay. Now, this v is just a velocity, which we can make it be anything. So let's let that be the speed of light. So we get E over c squared times c. C's cancel out. We get momentum equaling E over c. Now, we just said that energy is hc over lambda divided by c. C's cancel out. You get momentum equals h over lambda. If you solve that for lambda, you get h over p, which is h over mv. So, all he did, literally, he just took some ideas, all these ideas up here, and synthesized them into this. But this was the cool part about the predictive part of what he said. He says, hey, you know, if you have a mass, and this is only important when you get into masses that are really small, like the mass of an electron. So like this isn't relative to a baseball. So you got Planck's constant, 6.626 times 10 to the negative 34th joule seconds. Well, if you have a baseball with a mass of 0.1 kilograms and it's traveling at 10 meters per second, okay, which isn't all that fast, but here's what's going to happen. Well, this just becomes 6.626 times 10 to the negative 34th joule seconds. Or, excuse me, I screwed that up. This is the third time I've been through this lecture, so give me a little bit of a break here. That's meters. So if you have a baseball traveling at 10 meters per second, well, that's going to be its wavelength, which is an extremely, extremely small value, which isn't going to be anything noticeable. And if you make the baseball go faster, you get it up to 100 meters per second, then you're going to be dividing by an even bigger number, which is going to make the wavelength become smaller. So the faster things travel, the shorter the wavelength becomes. Okay, now we're going to do some more hocus pocus in terms of how energy is going to relate to this whole thing. So let's say that you've got lambda equals h over mv, and we know that kinetic energy is 1/2 mv squared. So to solve for this velocity, we get the square root of 2k over m. So, okay, before I get too far into this, I'm going to stop this because I got a sneaking suspicion that this isn't going to work. So I'm going to stop this for now, and then if it works, then I'll continue on the lecture. So I'm going to stop this, and then we'll take back up again.